All right, today we're going to start looking at testing a claim. It's another type of inference procedure. The previous unit, we looked at finding a confidence interval. We wanted to be able to estimate the population's parameter. We would say in confidence intervals, I am 95% confident that the true mean GPA of all seniors at this high school is between 3.2 and 3.5. Now we're going to test a claim. What that means is someone is going to make a statement about the entire population. Someone's going to make a claim about mu or p. And we are going to test that claim to see if we have evidence to support that, yeah, I believe that that's possibly true, or you know what? No way is this true. So someone's going to make a statement about a claim about mu or p. Okay. These, again, remember, are parameters. So when we test a claim, or we're going to talk about this as a significance test. When we run a test, the test must always be in terms of the null and alternative hypothesis. The claim will always be about the parameter, never the statistic. So we're going to try to use a statistic to gather evidence that supports or refutes the claim about the entire population's parameter. So again, we're going to use X bar to test mu, and we're going to use P hat to try to test to see if we believe P is true or not. So, what is a significance test? It's a formal procedure for using observed data to decide between two completing claims called hypotheses. The claims are usually statements about the parameter. I'm going to say that the claims are always statements about the parameter, P or mu. For example, here, a young man claims that he is an 80% free throw shooter. So this guy says, I shoot 80% free throws. We're not so sure. Do we believe him? Do we have evidence to support or refute his claim? So he's saying that his population parameter is zero point 0.8 or 80%. He's saying of all the free throws in the world that he shoots, every single one, he's going to make 80% of those free throws. Well, this season, he shot 50 free throws and he made 32 of them. So his sample proportion, P hat, the statistic, the data that we gathered for this season, we saw that he only shot 64%. Do we really believe him that he shoots 80% if he only made 32 out of 50? Do we believe that that's true? His claim is, yeah, you know what? I shoot 80% free throws. And what this is going to look like, this is going to be called the null hypothesis. So the claim is that P equals zero point 0.8. Well, we don't believe him. We don't think he can shoot that high. We think he shoots less than zero point 0.8. This will be what we'll see later is the null hypothesis and the alternative hypothesis. Many of the students will come to refer to this as the ho and the ha. Okay, the null hypothesis is the claim. It's always what they say is true. The alternative is what we're trying to gather data for. We're trying to find data to support this or to refute the claim that it equals zero point 0.8 and prove that really he doesn't shoot 80% of his free throws. Well, how are we going to do that? By gathering data. If the data that we gathered in our sample is very unlikely, assuming that the null hypothesis is true, then we'll have evidence against the claim. So in this case, I know this probably isn't realistic, but we simulated this like we learned back in the previous chapter. If he does shoot 80% of his free throws, what's the probability that he made 64% or fewer out of 50 shots? So this dot plot down here in figure 9.1 is illustrating that in 400 sets of 50 shots. So what we're saying is we had him shoot 50 free throws and we recorded what proportion or percent he made. And then we had him shoot 50 free throws again and we recorded it. And then we had him do that over 400 times he did that. Of those 400 times he shot 50 free throws, assuming that he does make 80% of all of his free throws, this is the distribution of the data set. So you can see each dot represents the proportion of free throws made out of 50 shots. So in real life, we did not have this young man shoot the ball over and over again. We simulated it by setting up the random integer and recording it on a calculator or a computer, and then graphed the percentage each time. So if he truly shoots 80%, as you can see circled down here, there were only 3 times that he was 64% or fewer, assuming that 80% is the true percentage that he makes his free throws. So if you think about that, 400 trials and only 3 times did he do as low as 64 or lower, if he really is an 80% free throw shooter. So 3 out of 400 times did that happen. So that's less than 1%. Okay? It's like 0.075%. Or if you like decimals instead, 0.00075. Whoops, that's one too many zeros, I think. So that's right, 0.075% or 0.0075. So if he really is an 80% free throw shooter, the probability of him getting a score of 64 or of 64% or fewer out of 50 shots would only happen about 7 out of every 1,000 times. Not very likely. If he truly shoots 80%, so the whole concept we need to be thinking about this unit is, if the null hypothesis is true, what is the probability of finding a sample such as the sample we found? If that probability is low, we will not believe the claim. If the probability is reasonable, then we cannot dispute the claim. And we'll get into the language of that earlier, like we talked about in statistics. We need to be able to speak the language. So either we will reject the null in favor of the alternative, or we will fail to reject the null, will be the language that we use. So that's basically what we're going to be trying to do for a significance test. Now, there's a formal process that needs to be done in order for us to make sure that we can trust our results from this significance test. So again, this whole unit, we're going to be looking at significance tests. Okay. Now, as we spoke to on the previous slide, then there's a null hypothesis and an alternative hypothesis. The claim that we want to find evidence against is called the null. So the null is written as H naught. And it's always going to be equals. Okay. So for right now, it's either going to be mu equals or it's going to be P equals, whether we're dealing with quantitative data or categorical data. The alternative hypothesis is HA. What we are trying to do is find evidence against the null and in favor of the alternative. So the alternative is written as HA. So it could be that we think that no, it's less, or we could be we're trying to test no, it's greater than, or maybe we just think, nah, you're lying, it's not equal to. And that would be the same for the categorical data. We could have that P is less than the claim, P is greater than the claim, or simply P is not equal to the claim. So this is every single null and alternative will be written this way. The null will always be equals, and the alternative will always be less than, greater than, or not equal to. We have, these would be called one-sided alternatives because we believe that it's on one side of the claim. Like the free throw example, we would say, P is less than, because we don't think he truly shoots 80%. Two-sided alternative would be, we're not sure, we just think that your claim is wrong. We don't know if your claim is, we don't know if you shoot less than 80% or more than 80%. We just don't believe that you actually shoot 80%. And in significance testing, just like confidence intervals, we're never going to be 100% sure. we're going to have evidence to say, I don't think this is true, or we're going to have evidence to say, I don't have enough to think this is not true. And we'll talk more about that as we move on. Let's take a look at an example real quick of how we would set up a null and alternative based off of an example. Okay. At the Hawaii Pineapple Company, managers are interested in the size of the pineapple grown in the fields. Last year, the mean weight of the pineapples harvested from a field was 31 ounces. Now they put in a different irrigation system in the field after the growing season. The managers wondered, would this new irrigation system affect the mean weight of the pineapples that are grown in the field? So by changing the irrigation system, did it change the mean weight of our pineapples? That's our test. Makes sense. You can see how this would be used in the real world, how this would be very beneficial to be able to run one of these tests. Now, just like in confidence intervals, there's going to be a 4-step process. We're going to look at the first step. So step 1 is always going to be define the parameter. What is this problem about? The mean weight. Oh, it's quantitative. So I know I'm going to be testing mu. Well, in this case, what is mu? Mu is the mean weight of the pineapples. Weird word, pineapple. Okay. So the mean weight of the pineapples. What pineapples? The mean weight of the pineapples grown in this field. When? This year. So we have to be very specific. We're going to be asking all year for you to put your answers in context of the problem. I can't just say mu is the mean. Mu is the mean what? The mean weight. The mean weight of what? The pineapples. What pineapples? The runs going in this field. When? This year. Okay, so be very descriptive when you're explaining the parameter. So step 1 is always going to be define the parameter. What is the problem about? Oh, it's about the mean pineapples of the weight, the mean weight of the pineapples grown in this field this year. Oh, okay, now I know what the problem's about. Now, the null hypothesis, H naught, the null hypothesis, the HO, okay? Since this is quantitative, it's mu. Well, what do we want to test? We want to test, did the new irrigation system change the weight of the pineapples? So my null hypothesis is that mu equals 31. The null is always, nope, there's no difference. It is as claimed. It is as historically it is known to be. So the null is going to be very easy to determine. It's always going to be, what do they claim, or what are we trying to test? Is it different? Let's find out. Okay, so the null mu equals 31 pounds. That's our null hypothesis, or our H naught, or the HO, as many of you are going to refer to it as. Then what is the alternative hypothesis? What does the farmer want to see? Does he want to see if his pineapples got heavier? If they got lighter? No. The question says the manager wonders if this change will affect the mean. Will it affect the mean? It doesn't say he wonders if his pineapples will get heavier or get lighter. He just wants to see if his pineapples have changed due to this new irrigation system. Therefore, the alternative would be two-sided. So when we say one-sided and two-sided, you can think about one-sided on the left or the right. Two-sided, we're going to have to look at the area in both tails. We're going to go back to our normal curve and use our z-scores and our normal curve to find these probabilities to answer these questions. Okay. All right, and how are we going to do that? Well, if the data is rare, how rare? Well, that's where the p-value is going to come in. The p-value is the probability of obtaining a result as extreme or more extreme, assuming the null hypothesis is true. So we're going to always run a significance test under the assumption that the null is true. With that assumption, we're going to draw our favorite picture. We're going to end up drawing our normal curve. We're going to put the null hypothesis as the mean, and we're going to find the standard deviation, 1, 2, 3, 1, 2, 3. We're going to do our z-score calculations. We're going to look it up in a table, and we're going to find if the null is true, what is the probability of finding a result such as the result we found? If that probability is low, then I don't believe the claim. If that probability is high, then I do not have enough evidence to not believe the claim. And the book's definition of a p-value, the p-value of a test is the probability of getting evidence for the alternative, HA, as strong or stronger than the observed evidence when the null hypothesis is true. So think about the p-value is assuming the null is true. The p-value is the probability of finding a sample as small or smaller than the sample we found. That's another way to think about this p-value. Okay, you might think, oh, Claycamp, you sucked writing on this computer screen. Well, you know what? If you were in the classroom and I was writing on the whiteboard, it wouldn't look much better. Okay, so it's not, I can't blame it on technology, it's operator error. So what is the p-value? Assuming the null hypothesis is true, what is the probability of finding the result as small or smaller than the result we found? Or assuming the null is true, how rare is this sample? If it's rare, then I don't believe you. Okay? If I claim that my mean number of push-ups I can do each day is 100, and you say, all right, cool, let's gather some data. Go out and do your push-ups today, Claycamp, and I do 10. And the next day I do 15. You're going to say, yeah, you know what? If you could really do 100, the probability of you only being able to do 10 or 15 is very small. Therefore, I don't believe your claim. In other words, that's what we're trying to do. So let me clear out my own definition of the p-value so that we can look at an example here. Now, calcium is a vital nutrient for healthy bones and teeth. The National Institute of Health recommends the calcium intake of 13 milligrams per day for teenagers. The NIH is concerned that teenagers are not getting enough calcium. On average, is this true? Researchers decide to perform a test. So remember, the null hypothesis, H naught, the HO, is always going to be what is claimed. There is no difference. Nope, there's no difference. The null is, let's test, are these teenagers really getting 1,300 milligrams per day? The researcher is concerned that teenagers are not getting enough calcium. So the alternative hypothesis that we want to test is that mu is less than 1,300 milligrams. Okay. So where mu is the true mean daily calcium intake. So remember, we always must define the parameter. Mu is the true mean daily calcium intake for who? Teenagers. So that's what we're trying to test. It's the true mean for all teenagers in the world. Well, there's no way we can ask all teenagers in the world. So what we're going to do is gather a SRS, or a sample of teenagers. And from that sample, if the data is relatively plausible, if it's the probability of it occurring is pretty common, then okay, we believe that they're getting enough. If that sample is way far away and gives us a very small p-value, or the probability of that occurring, assuming these people are really getting 1,300, is small, then we will not believe the claim. So they ask an SRS of 20 teens to record their food and drink consumption for a day. The researchers then compute the calcium intake for each student. So they come up with statistics. Their statistics, X bar, is 1198. So on their sample of SRS of 20 randomly selected teenagers, they had a mean intake of 1198. Well, it's clearly not a mean intake of 1,300, but is it rare? If this 1198 that we found is very unlikely, assuming the null is true, then we would have to reject their claim, or we would reject the null hypothesis. So the statistics they found was that the mean was 1198 with a standard deviation of 411. Okay. Researchers performed a significance test and came up with a p-value of 0.1404. What does this p-value mean in context of the problem? Moving forward here very soon, we'll look at how did they calculate that p-value? Where did it come from? What kind of statistics or mathematics were involved in calculating that value? But right now, it's super important that we can interpret the p-value in context of the problem. Okay, that's going to be a huge part of significance tests as well as confidence intervals, is the interpretation in context. So remember, we always define the parameter, and we said that mu in this case is the mean. The mean what? The mean daily calcium intake. The mean daily calcium intake of who? Oh, of teenagers in the United States. So remember that we need to be very clear on what it is that we're about to test. What is mu? So a p-value of 0.1404. Explain what it would mean for the null hypothesis to be true in this setting, and then interpret the p-value. So our two problems are down here. Explain what it would mean for the null hypothesis to be true in this setting. If mu equals 13, then the true mean daily calcium intake for teenagers in the US would be 1,300. So part A, that's what it would mean. Explain what it would mean for the null to be true. If the null was true, then teenagers in the United States really did on average take in 1,300 milligrams of calcium per day. Okay. Interpret the p-value. This is probably the most important part of this whole significance testing, because if we don't know what our results mean, then we're wasting our time. So what does this 0.1404 mean? It says, assuming the null is true, okay, under the assumption that teenagers really do take in 1,300 milligrams of calcium per day, there is a 14% chance of finding a sample of 20 students which the calcium intake would be 1198 or less. So if this 1,300 really is the true mean for all teenagers in the United States, the probability that we find a sample as small as 1198, or smaller would happen 14% of the time just due to chance alone. Just due to sampling variability, we would expect to get a sample mean X bar of 1198 or smaller 14% of the time. So therefore, we do not have enough evidence to claim that the teenagers are not getting enough calcium. Because if they truly were getting 1,300, the probability of getting a sample of 1198 or smaller would happen 14 out of every 100 samples. Therefore, I do not have enough evidence to reject the null. Okay. Now, we never can say we accept the null. We can just say that we fail to reject the null. We'll get into that more soon here. So assuming that the mean daily calcium intake in the teen population is 1,300 milligrams, there is a 0.1404 probability of getting a sample mean of 1198 or less just by random chance. Therefore, yeah, okay, maybe they do get 1,300. I don't have enough evidence to say that they do not. Super important that we define the parameter in context, and that we can interpret the p-value. Well, we said that 14% was not enough to refute the claim. Well, if it happens 14% of the time due to chance alone, then I can't say that it's wrong. Well, when then can we say that it's wrong? When can we say, yeah, you know what? I have strong evidence that the null hypothesis is incorrect. I do not believe that this is true. And we're going to use the significance level, or the alpha level. I call it the little Jesus fish. Okay, we're going to use this little guy right here. That's the level that we're going to test the p-value against. Okay, so if the p-value is small, how small? Less than the alpha level, then we would reject the null in favor of the alternative. So how small does that p-value have to be? It has to be less than the predetermined alpha level. If the alpha level is not given to us, we will use 5%. So the standard, if the alpha level is not given, then we will assume that the alpha level is 5%. So the alpha level is the boundary point, the cutoff point. If p-value is less than alpha, reject. If the p-value is greater than alpha, fail to reject. The standard alpha is 0.05 if it's not given to us. So how do we know whether we're going to reject the null or not? If the p-value is smaller than the alpha level or the significance level, we reject the null. If the p-value is found to be greater than the alpha level, in context, mind you, we will say we fail to reject the null. We never accept the null. Okay, we're never going to say we accept the null. Think about it. You can't accept the hoe, right? We reject the hoe, but we can't accept the hoe. Okay, if the p-value is small, reject the null and conclude that there is convincing evidence in favor of the alternative. If the p-value is not small, we fail to reject the null and conclude that there is not convincing evidence that the alternative is true. So we either reject the null or we fail to reject the null. We never accept the null. So this alpha level is our cutoff point. In the previous problem, we said, how rare is too rare? If the p-value is 0.14, does that prove that the null is false? The alpha level is going to give us that cutoff point so that we can make that determination between rejecting and failing to reject the null. Okay. Let's take a look at this example. A company's developed a new deluxe AAA battery that's supposed to last longer than its regular batteries. However, these new batteries are more expensive for the company to produce. So they need to be convinced that they really do last longer. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours. The company selects an SRS of 15 of their new AAA batteries and uses them continuously until they are drained. The sample mean lifetime is 33.93 hours. So they're going to perform a significance test. So they do. They run this test. What test are they running? Well, I forgot. How do we start every significance test? By defining the parameter of interest. What is this problem about? Mu is the true mean life of the new deluxe AAA batteries. Always we start with defining the parameter. Okay. Whoops, I don't need that I in there. Okay, the true mean life of the new deluxe AAA batteries. Now, what does this company want to find out? They hope that this new deluxe battery lasts longer. So the null is always, no, there is no difference. It is as stated. the alternative, what do we want to find? That they're different? No, we hope to show that they are greater than. Okay, so we ran the test. They had a statistic, a sample mean X bar of 33.93. How rare is that? Well, I don't know. It's definitely not equal to 30, but is it far enough away from 30 for us to conclude that it does last longer than the original batteries? Well, we have to go through the process of calculating the p-value. And then remember, we can compare the p-value to the significance level or the alpha level. So in this problem, they've done all the work for us already, and they have a p-value of 0.0717. What conclusion would we come to based on an alpha level of 0.05? So if alpha equals 0.05, is this p-value 0.0717 smaller than 0.05? No, it's not smaller. Therefore, we fail to reject the null. We do not have enough evidence to conclude that this new battery lasts longer than the original battery. So since it cost the company a lot more money to make this new battery, there's not enough evidence to say that it's worth their time for changing their production process and spending extra money, because if this new battery was the same as the old battery, so we're always looking at every p-value as the assumption that the null is true. So if this new battery does have a mean lifetime of 30 hours, the probability of finding a sample mean of 33.93 or larger, why are we saying larger? Because the alternative is greater than, would happen 7% of the time just due to sampling variability, just due to chance alone. We know that every single battery is not going to last exactly the same length as the battery before. Okay. So again, real quick, as a review of the p-value idea. If the p-value is larger than the alpha level, we fail to reject. If the p-value is less than the alpha level, the data is, we're going to talk about it being statistically significant. That it's, if the p-value is less than the alpha level, the data is statistically significant, and we would reject the null in favor of the alternative. Since this p-value is larger than this alpha level, we fail to reject. We do not have enough evidence to conclude that these new batteries last longer. I know this is a lot of stuff we're talking about here, but it's super, super important that we go through all of this and understand how to talk about the null and alternative, how to reject, fail to reject, and when all that happens. And more importantly than that is, why does it happen? Why are we making these statements and these claims?